Welcome to the deep dive. Today, we're tackling a really fascinating intersection, how artificial intelligence is shaking up network technology.
Yeah, it's a big one. We're looking at how AI is being woven in to make networks smarter, faster, more efficient.
Especially as we look ahead to things like 6G, right? We've got some great sources here giving us the whole picture from what's happening now to, well, what's on the horizon.
That's right. And for you listening, someone who wants the real insights without getting totally bogged down in jargon,
Yeah.
our goal is to pull out the most important stuff. Think of AI as this incredibly powerful toolkit enhancing networks in, well, loads of different ways.
Exactly. So the big questions we're really diving into are how exactly is AI being used now, and how is it envisioned to improve networks?
And looking forward, what are the key research areas? Where's the cutting edge in this field?
Okay, let's get into it. Let's start with how AI is improving the networks we already have. This isn't about ripping everything out, more like adding smart upgrades.
Right. It's like intelligent patches, almost. AI is acting as this optimization engine for current networks.
Boosting performance, efficiency.
And ultimately, just a better experience for us, the users. We're seeing this already in a few key places.
Like spectrum. Radio spectrum is limited, right? Finite.
Absolutely.
Yeah.
And AI's predictive ability here is, well, it's a game changer. It can actually forecast traffic peaks.
Like everyone's streaming the World Cup final at once.
Exactly that. And it can proactively shift spectrum resources around to handle it, to stop things grinding to a halt.
And that connects to making networks greener too, doesn't it?
It does, yeah. That's a really interesting link. These networks, especially 5G and beyond, they use a lot of power. AI can look at real-time demand and tell a base station, hey, it's quiet now, power down a bit.
So you're not running everything at full tilt 24/7.
Precisely, which means real energy savings, lower carbon footprint. It's a win-win.
That's huge. And this AI optimization, it goes beyond just the signals, right? And what about running the network itself? Managing and maintaining it? That sounds incredibly complex.
Oh, it is. Traditionally, yeah. Lots of manual checks, troubleshooting after something breaks, slow, expensive.
Reactive.
Exactly. AI allows a shift to being proactive. It analyzes network patterns, spots anomalies.
So it can flag a potential problem before it happens.
That's the goal, predictive maintenance. It minimizes downtime, makes the whole operation much more efficient. And that's crucial as networks get more complex with virtualization, edge computing, all that.
Makes sense. Managing complexity with intelligence. And for us, using the network, what does AI mean? More personalized service.
Yes, definitely.
Yeah.
Networks need to handle such diverse demands now. A simple voice call is very different from, say, Ultra HD streaming or critical IoT data.
Right. Different needs for speed, latency, reliability.
And AI helps the network understand those different needs and actually tailor the service. You can adjust data rates, latency, reliability dynamically for each specific application.
So moving away from one size fits all.
Towards something much more adaptive and user-centric.
And of course, security. Always a big concern. AI is helping there too.
Oh, massively. Its ability to crunch vast amounts of network data in real time is perfect for security.
How so?
It can spot weird patterns, potential threats that older methods might miss entirely. It means you can be more proactive about security, not just reacting after an attack happens.
Okay, so it's clear AI is already a powerful enhancer for today's networks. Let's dig a bit deeper into how it's doing this. The specific techniques, you mentioned traffic prediction.
Yeah, that's a big one. Understanding how traffic flows change over space and time, spatiotemporal patterns, we call them.
Right.
Models like RNNs, recurrent neural networks, and LSTMs, long short-term memory networks, are really good at this. They have a kind of memory to understand sequences.
Like understanding traffic patterns on your commute over time.
Exactly like that. They learn the dynamics. But collecting all that data centrally raises privacy flags. Yeah.
Right. Which is where federated learning comes in.
Precisely. Federated learning is a huge deal here. Instead of sending raw traffic data to a central server,
which people might not want.
Understandably. Instead, the AI models are trained locally, right there on the edge devices or local servers.
And only the learnings, the model updates are shared, not the actual data.
Exactly. Only the aggregated parameters. It's a fundamental shift for privacy-preserving AI on networks. We're even seeing refinements like distance-weighted federated learning to better model geographic relationships.
Clever. And to speed things up, transfer learning.
Yeah, that helps too. If you've learned traffic patterns in one city, you can transfer some of that knowledge to help train a model faster in a similar city. Reusing knowledge, basically. Saves time, saves computing power.
Okay. And what about the energy saving side at base stations? You mentioned reinforcement learning, RL.
Right. RL is where the AI learns by trial and error. It gets rewards for good actions.
So it figures out the best setting.
Exactly. It can learn to dynamically adjust base station parameters, power levels, sleep modes based on real-time conditions. It can even figure out the best way to integrate renewable energy sources if they're available.
Leading to real carbon emission reductions.
The studies show potentially significant savings, yes. It's a powerful optimization tool.
Very cool. Okay, what about when I'm, say, on a train and my phone switches between cell towers, handoffs? AI helps there too. We all hate dropped calls.
Definitely. AI-based mobility management. Deep Q networks, or DQN, which is a type of deep reinforcement learning, are used here.
To make the handoff smoother.
Yeah, to optimize it. Reduce problems like ping-pong handoffs where you bounce back and forth rapidly between two towers.
Annoying.
Very. Especially in fast-moving scenarios or dense areas. AI also helps manage handoffs between different frequency bands, like switching between the lower sub-6 gigahertz bands and the faster milling wave bands.
So it's working behind the scenes for seamless connectivity. And does this intelligence extend to allocating all the network's resources? Bandwidth? Computing power?
Absolutely. Think about these really complex future networks, integrating satellites, drones, ground stations, multiple layers of computing.
Space, air, ground integrated networks. It sounds complicated.
It is. And RL is being used to figure out the best way to jointly schedule both communication resources, like bandwidth, and computing resources across this whole complex system.
So AI decides where and when to allocate everything.
Intelligently, yes.
Huh.
It's also key for network slicing, creating those dedicated virtual network slices for specific services and for dynamic spectrum allocation, assigning spectrum on the fly based on need. It's like a super intelligent network manager.
A digital air traffic controller, but for data and computing. And last point on enhancing current networks, security defenses.
AI is a massive boost here. Machine learning models, including transformers, which are great at understanding context in sequences.
Like in language models.
Similar underlying tech, yeah. They're used for anomaly detection, spotting things that just look wrong on the network, potential attacks. Also for intrusion detection, identifying active attempts to breach the network, and even predicting potential future security issues based on current trends. And beyond attacks, it helps find and diagnose regular network faults faster, too.
Right. So AI is already adding this really significant layer of intelligence to today's networks. But now let's shift gears. 6G and this idea of network for AI, net for AI. This sounds different, like the network itself is being designed to run AI.
It's a fundamental architectural shift, exactly. The vision for 6G isn't just about faster connections. It's about building an AI-native network.
AI native.
Meaning AI capabilities, especially distributed computation, are baked into the network design from the ground up. It's moving from being just pipes for data to being a platform that actively enables and supports AI processes.
That's a big leap. I know different groups have proposed blueprints for this. Can you give us a flavor of what they look like? How do they embed AI?
Sure. There are several interesting proposals. China Mobile talks about 3 layers and 6 planes, focusing on multidimensional capabilities. China Telecom has 3 layers and 3 sectors, aiming for intelligent simplicity. China Unicom envisions layers across land, air, and space with intelligent native chains. Huawei proposes a task-centric AI architecture, focusing on coordinating resources for specific AI jobs.
Right.
OPO sees AI as a ubiquitous underlying infrastructure. And the IMT 2030 6G group in China talks about an open platform offering computing, security, sensing, data, and AI autonomy as core network services.
So the common thread is really deep integration. AI isn't just running on the network, it's part of the network.
That's the core idea, embedding intelligence right into the network fabric.
Okay, so what technologies make this network for AI possible?
Several key enablers. One huge one is distributed intelligence, and federated learning, FL, is central to that.
We touched on FL earlier for privacy and traffic prediction.
Right. And here it's even more fundamental. The need for low latency, high reliability, and privacy means intelligence needs to be closer to where the data is generated at the edge.
And FL lets you train models across many devices without moving the raw data.
Exactly. It's crucial. You train locally, share only the model updates. We see horizontal FL, same data types, different users, like for personalized services.
Or hospital collaboration.
Right. And vertical FL, different data types on the same users, maybe combining telco data with app data to build richer models. But FL isn't perfect. There are challenges like getting models to converge well, handling data variability.
And you mentioned other distributed techniques too, MRL and SL.
Yes. Multi-agent reinforcement learning, MRL, is for scenarios with lots of interacting agents. Think coordinating self-driving cars in a smart city. Each agent learns based on its goals and what others are doing.
Okay.
And split learning, SL, is interesting for devices with less power, like basic IoT sensors. You split the AI model, part runs on the device, part runs on a server, helps with privacy and resource limits.
But maybe has its own security issues.
Potentially, yes. Needs careful implementation. So it's a toolkit for spreading intelligence around.
Got it. Another concept was digital twins for 6G, virtual copies of the network. How does that help AI?
Digital twins are incredibly powerful. They're dynamic virtual replicas of the physical network.
Like a simulation.
More than just simulation, it's constantly updated with real-world data. So you have this accurate virtual copy where you can test things, optimize AI algorithms, predict problems, try out new configurations.
Without messing with the live network.
Exactly. It's a safe sandbox. You can really hone AI-driven management strategies, predictive maintenance, resource allocation, all in the twin before deploying it for real. We're seeing it used in vehicular networks, too, for simulating traffic and services.
That sounds incredibly useful for managing something so complex. Then there was the computing power network. What's that about?
This is the idea that the network itself becomes a way to find and use computing power from anywhere. Cloud, edge servers, maybe even idle user devices.
So the network doesn't just move data, it moves compute jobs to where the power is.
Essentially, yes. It acts like a broker or orchestrator for compute resources. The key ideas are: discover available power in real time, schedule jobs flexibly onto those resources, and give the user or application a seamless experience, regardless of where the calculation actually happens.
And things like in-network computing, INC, fit in here, doing some processing within the network switches and routers.
Yes, INC can help reduce latency by processing data closer to the source. And you might see technologies like blockchain used to manage trust and security in this distributed compute environment.
So connecting data, devices, and compute power. Okay, and the last piece was secure multi-party computation, SMPC.
Right. With all this distributed data and AI, how do you compute things together without revealing your private data to others? That's SMPC.
Cryptography.
Exactly. It uses cryptographic techniques, things like garbled circuits, secret sharing, homomorphic encryption to let multiple parties jointly compute a result, like aggregating model updates in FL, without any party seeing the other's raw inputs.
So collaborative AI without sacrificing privacy.
That's the promise. It's vital for things like secure FL aggregation, or maybe allocating resources based on sensitive business data from different companies. It has overheads, computationally, but offers strong privacy guarantees.
Okay, that paints a picture of a very different kind of network, which leads us to the third stage, AI as a service, AIS. This sounds like the network isn't just supporting AI, it's offering AI capabilities directly.
Precisely. This is the ultimate goal, really. Ubiquitous intelligence. The network transforms into a distributed AI service platform.
Like cloud computing offers storage or compute, the network offers AI functions.
That's a good analogy.
Mm-hmm.
It shifts from being purely connectivity-focused to being service-oriented with AI as a core offering.
What would that look like in practice? Give us some examples.
Okay, think about immersive communication VRR meetings.
Yeah.
AI could provide real-time translation between languages on the fly,
Right.
or analyze sentiment and expressions to improve understanding. Maybe offer personalized suggestions within the virtual environment. For industry, think hyper-reliable, low-latency communication for robots or remote surgery. AI constantly optimizing the connection for those critical needs.
Right.
For massive IoT and smart cities, AIS could provide the tools to manage and analyze data from millions of sensors. For intelligent transport, it could offer data services to autonomous cars, offload heavy computations, predict hazards.
So the network becomes this intelligent toolbox applications can draw from. How do you measure if these AI services are any good, though?
Great question. That's where this idea of quality of AI service, co-AIS, comes in.
Co-AS?
Yeah, it's a framework to evaluate these network-delivered AI services. It goes way beyond just checking if the AI model is accurate.
How so?
It looks at the whole picture. How well does the model generalize? How robust is it? What's the quality of the network connection supporting it? Is the compute resource reliable? Is the data private and secure? How well is this service orchestrated? It's a holistic view of the end-to-end AI service quality.
Okay, that makes sense. It's not just the algorithm, it's the whole delivery system. What capabilities does the network need to actually deliver this AIS?
Three main pillars, really. First, strong data support and model access. The network needs to gather real-time data, securely and privately, of course, and give users easy access to AI models, maybe pre-built ones, or allowing custom model.
Data and models readily available.
Second, distributed computing and smart resource optimization. Using all that compute power spread across the 6G network, cloud, edge devices, and intelligently allocating it using things like software-defined networking and AI techniques like DRL.
Got it. Smart resource management.
And third, robust security and lifecycle management. Protecting the data, authenticating devices, securing the AI models themselves from tampering or theft, all the way through their operational life. End-to-end security.
It's a really ambitious vision, which brings us to what research still needs to happen to get us there. What are the big open questions?
Oh, plenty. It's a very active research area. One key thing is developing better adaptive learning mechanisms, AI that can learn and adjust on the fly in dynamic network conditions, enabling self-healing, self-optimizing networks. Think more advanced DRL, transfer learning.
Smarter adaptation.
Another is designing the network architecture itself for this inherent flexibility. How do you best build networks that support edge computing and federated learning natively?
And sustainability must be a big one. Green AI.
Huge. Developing energy-efficient AI models and network hardware is critical, plus integrating renewables seamlessly. We also need more research into AI specifically for ultra-low latency communication lightweight models for the edge, AI-driven orchestration for those real-time critical apps.
You mentioned wireless network large models earlier, like large language models, but for networks.
Kind of, yeah.
Yeah.
Adapting these massive AI models for the wireless domain presents unique challenges. How do you design their architecture for distributed networks? What kind of data sets do you need? How do you get real-time performance? Lots to figure out there.
Okay.
Then there's applying AI to specific 6G technologies. Intelligent reflecting surfaces, IRS, to steer signals, integrated sensing and communication, ISAC, Open RAN, non-terrestrial networks like satellites. AI can optimize all of these.
And finally, ubiquitous computing, delivering AI everywhere.
Exactly. Designing resource allocation schemes that work across these complex, heterogeneous networks, ground, air, space to provide AI services seamlessly anywhere in the world, that's a major challenge.
Wow. It really underscores that AI isn't just an add-on, it's fundamental to where networks are going.
That's absolutely the key takeaway.
Yeah.
AI is becoming deeply woven into the fabric of network evolution, especially with 6G. It's driving huge gains in efficiency, intelligence, and what networks can actually do.
And those three stages you outlined, AI for the network for AI, and AI as a service, really show that progression, don't they? It's a deepening relationship.
It is. And you see this reflected in the global standardization efforts, too.
Yeah.
There's huge momentum behind this convergence internationally.
But it's not all solved yet. There's still significant hurdles, as you said.
Definitely. Ensuring AI reliability in these complex systems, managing resources efficiently, sustainability, meeting real-time demands, security and privacy remain huge challenges, and also how humans interact with and manage these increasingly intelligent networks. Lots of room for innovation still.
Well, this has been incredibly insightful, a real deep dive into how AI is reshaping networks, from enhancing what we have today to powering the entirely new capabilities of 6G.
It's a fascinating space, absolutely. The potential impact is enormous, far beyond just faster downloads.
Right. And on that note, maybe a final thought for you, our listener, to mull over. As AI and advanced networks like 6G become this tightly integrated, ubiquitous intelligence layer, how will that fundamentally change things? Not just communication, but potentially blurring the lines between our physical and digital lives. What new possibilities and maybe what new challenges does that truly interconnected future hold? Thanks for joining us for this deep dive.